In this video, we're going to recognize or work through what the hard part is in the fundamental theorem of calculus. So we've done antiderivatives, and if we have an integral that we want to evaluate, our first step is to find this capital F of x, which is an antiderivative of what we were given inside the integral. The problem is that's not always easy. For now, we're going to stick with simple antiderivatives, but even with more complicated techniques, this is going to turn out to be a hard first step. This, starting with an f of x and getting an antiderivative, is going to be surprisingly challenging. Harder on average, I would say, than taking derivatives. As a first remark about this process, we motivated all our integral calculations by doing an integral on an interval from a to b with bounds. However, it's going to be useful just to say, how can I talk about antiderivatives without just saying the word antiderivatives? We're going to introduce this new notation with no bounds. We're going to call this an indefinite integral, and it's going to be what we mean by the antiderivative. Just that one part. And again, this is a pure notation idea. The idea is, if we have to find antiderivatives a lot anyway, and we want to focus on that problem, let's invent a notation. And it's essentially the analog of the derivative of f of x. This is the differentiate, find the slopes of f of x. This is find a formula for the antiderivative of f of x. This is find a formula for the antiderivative of f of x. An important note is the definite integral is a number. If you integrate from a to b some function, you're going to get 7 or 150 or 5. But the key thing is it's a number. Whereas if you integrate without any bounds, something like x squared, then we're going to find the antiderivative of x squared. That would be, in this case, adding 1 to the power, dividing by the new power, potentially adding a constant. This is a function. So the kind of answers you get back from definite integrals, where we get a value, versus indefinite integrals, where we're just interested in the antiderivative function itself, these should look quite different at the point where you stop doing your calculations. Going back to that plus c, we will include that in our indefinite integral every time. So by default, if you see an indefinite integral question, find the antiderivative, that's sort of the easiest, and then always add the plus c at the end. You will lose marks if you forget the plus c. What I've seen frequently on tests is that people will put a big plus c on their front page. By all means do that if it helps as a reminder. Again, thinking in the notation of how we compute, taking a step back. As a third point, if you think of the steps of evaluating an integral with limits of integration, the fundamental theorem of calculus says we need to compute f of b minus f of a. And so there's really 3 steps. And so there's really 2 steps to that. One is getting the antiderivative. So if we're faced, say in this example here, the integral of x squared from 0 to 4, one step is the antiderivative process. And so we often want to evaluate that first. Well, we add 1 to the power, divide by the new power. And then we also can't forget, though, that we need to sub in the 4 and sub in the 0 in this case, f of 4 minus f of 0. Or we remind ourselves to do that with this vertical bar and placing the 4 and 0 values at the upper and lower ends of this. And that just means evaluate it at 4 and then subtract, evaluating that function at 0. This vertical bar then gives us a notation that separates the antiderivative from the f of b minus f of a calculation, and just gives us a reminder along the way of what we still need to do. As a final remark, it's a surprising but useful note to make that when we integrate over an interval, our function f of x dx, we call the x variable here the variable of integration, and if we're doing a definite integral, it doesn't matter what it is. If we draw this out, imagine drawing out an example where we have x and a function f of x, and an interval from a to b. We're talking about the numeric value of the area underneath that graph. Well, it doesn't change anything if we called this f of u and then relabel this axis u, or time, if we call this f of t and relabel this axis time. The area that we would encounter here does not change. Call it theta and theta. So for definite integrals, you can change these variables and it won't change the value. That's not true with indefinite integrals. Let's go back a step. If we integrate x squared with respect to x, we should get a function of x's back. But if we're taking that final step and subbing in values, like in this case here, if this had been u squared du, we still would have ended up with this calculation at the end of the day. So with that all considered and thought through, we can now progress to more applications and more challenging integral calculations in the course.